introduction, and thank you for the invitation. In front of many experts of MCMC and SMC in your department, I cannot say I'm an expert, but I would like to share some of my recent work using the sequential Monte Carlo methods for estimating parameters from differential equations. So here is the outline. I will first give an introduction to the problem, and then I will talk about some existing methods for estimating differential equation parameters, and then I'll talk about our proposed method for doing Bayesian inference using SMC, and then I'll show you some simulation and application results. So let me first give you a motivating.
Sorry to disturb you. I don't know if it's only me, but I still see your slide 1. So in case you shared slide.
Okay, I'll stop share and share it again to see whether. Okay.
Okay, perfect. Now is the slide on population. Yeah,
okay,
slide 4.
Thank you for letting me know.
You don't know if you want. I mean, you might start from before as you wish.
It's okay. So this is the first page. Let me first give you a motivating example. So Nicholson published his classic study on the competition for food in lab populations of Australian sheep blowflies. The blowflies were cultured in a room maintained at 25 degrees Celsius. He measured the population of blowflies every day for approximately 1 year. So this is the data. So basically, we have the counts of blowflies versus time in the unit of days. So the population, the blowfly population x of t can be described using this differential equation where we have x of t represent the blowfly population, where we have this R, that's the rate of increase of the blowfly population. That's a parameter P, which is the resource limitation parameter set by the food supply. There's one special parameter tau, which is a time delay. It's roughly equal to the time for a larva to grow up to an adult. So this differential equation is called the delay differential equation. It's one special, it's just one differential equation, delay differential equation, or in short, DDE. So in a more general notation, so we may have multiple differential equations. So we are going to use subscript I to denote the S differential equation. And for each one, it's the derivative of xi of t with respect to time t, which can be described using a parametric form. Here I'm using this G sub I to denote this parametric form. So this is related to x of t and x of t minus tau. So you can see here, so it also relies on some history of the process. And this depends on some parameter theta. I'm using the this notation theta to denote the vector of parameters describing the system. So in case tau is equal to 0, so this DDE becomes an ordinary differential equation, because ODE is a special case of DDE. So I'm going to use the notation for DDE in this presentation. So we can only observe some noisy data, or we can only partially observe the data. So use this y to denote y sub ij to denote the jth observation of the s differential equation xi at time ti. We assume a likelihood function, which is usually said to be normal distribution, and there are some related parameters in this observation model. So I will use this theta sub y to denote the parameters in the likelihood function. So for example, if we assume the observation yij follows the normal distribution with mean xi at time tij with variance sigma I square. So in this case, we have this theta sub y, which is the parameters in the observation model, includes theta 1 square until theta sigma 1 square until sigma I square. So this is the notation for the observation model. So the challenge is that we need to estimate all these parameters, including theta and the delay parameter tau and the initial state from noisy or partially observed data. There are several challenges. Usually we have to use numerical solvers to solve these differential equations. So there's no analytic solution. So we have to solve them numerically. Another challenge is that the DDE solutions will not only depend on the parameters theta and tau, but also rely on the history of the dynamic process. So we use h sub tau to denote this process x of t when t is before the first observation time t1. So this t is from t1 to t1 minus tau to t1, which is an infinite dimensional set. Another challenge is the DDE solutions are extremely sensitive to the delay parameters. So that's a parameter tau in our notation. So there are several methods can deal with this parameter estimating problem. So the first method is MLE. The DE parameter theta can be estimated by maximizing the log likelihood function. So here we have this log likelihood function, and if we have a small n observations, so we just need to write down this log likelihood function and maximize it with respect to the parameter, all the parameters. So in this part of slide, so I'm simplifying the notation theta to denote all the parameters in the problem. However, the difficulty with this MLE is that the DDE solution is an implicit function of theta. And the numerical solver might be computationally expensive to use. There are also some many local optima in the log likelihood. It's not easy to optimize it. Also, we needed to specify the unknown history of the dynamic process, h sub tau, to solve the DDE numerically. Usually, people choose this history to be the first state. It's just an approximation. Another method is called a two-step procedure. In this two-step procedure, first we do the non-parametric smoothing. So we can estimate x of t and the derivative x of t from noisy data using non-parametric smoothing methods. And then we can do the nonlinear regression to estimate the parameter theta and the tau. The advantage of using this method is we don't need to solve DDE, so it's faster in terms of computation. However, the drawbacks are the derivative of x of t may not be well estimated, especially from sparse data. Therefore, the parameter estimation is not accurate. So that's why many years ago, so we proposed a semi-parametric method. And in this method, we don't need to solve the DDE numerically. We don't need to specify the DDE history, and the estimation is more accurate than the two-step method. What we did is that we approximate the DDE solutions by a linear combination of basis functions. That is, we represent this x of t using some basis functions phi of t and their coefficients c sub k for the kth basis function. So here, phi of t is a vector of basis functions at time t. For example, we can use B-spline basis functions, and c as a basis function coefficients. The is a typo here, so that's basis function coefficients. Here I'm showing you one example of the B-spline basis functions. You can see each curve represents one basis function. So in terms of the estimation of the parameters, so here, besides the parameters in the DDE, we also need to estimate the coefficients to the basis functions. So in order to estimate the basis function coefficients and the parameters, so we consider two criteria. One is fitting to data. So we have our observations yi, and we have our non-parametric function x of t represented using the basis function expansion. And the fitting to data is evaluated using the log likelihood function. And we can represent this part as C1, and the second part is fidelity to the DDEs. So we have the form of our DDE, and we take the difference between two sides of DDE, and we do the integration of the squared difference between the two sides of DDE, and we put the two criteria together using a tuning parameter or smoothing parameter lambda. So to estimate the DDE parameter theta, so we consider the criterion using the log likelihood. So with some detail, so this is involve two nested levels of optimization. So in the inner level, so we can get estimator for C, which can be expressed as a function of the DDE parameter theta. So we have C hat of theta. And in the outer level, so we plug in the estimator for C, and we optimize the log likelihood function. So now it's become a function of theta, and we get estimator for theta. So basically, this is a diagram of the estimating procedure. So it's a nested optimization. For the smoothing parameter, so it was estimated using the k-fold cross validation method. However, we can get the point estimation from this frequentist method, and we used the bootstrapped method to get the standard deviation for the point estimate. But that estimate is underestimated. So that's why we would like to use a Bayesian inference for the parameters in DDE so that we can get the uncertainty estimation. And also we would like to have a efficient computation. So that's why we are proposing to use the SMC Monte Carlo methods for Bayesian inference. So in this case, so we are looking at the posterior distribution of the parameters in the DDE. So here I'm using this theta sub DE to denote both the parameter theta and the delay parameter tau in DDE, and using theta sub Y to denote the parameters in the likelihood function. So C is the coefficients of the basis functions, and lambda is the smoothing parameter. So in this case, so we're using the prior distribution for C to serve as a so that corresponds to the penalty term in the frequentist method I just introduced. I'm using this pi to denote our normalized posterior distribution, and using gamma to denote the unnormalized posterior distribution, which is equal to the likelihood times the prior, which I'm going to introduce in a minute. So the prior distribution for C given lambda, theta, and tau is in this form. As you can see, basically it's almost the same as the, so this part is almost the same as the penalty part in the frequentist method. So here, so the prior distribution so serves the same purpose, which is to measure how well the estimated differential equation variables satisfy the differential equation system. And we can specify some prior distribution for theta and for lambda. So here, just one example that we can use. So for the likelihood function, if we use a normal distribution, so that's the form of the likelihood function when we have when we use a normal likelihood. Okay. So we're using the SMC method. So in the SMC method, we needed to propose a sequence of intermediate distributions. That's because it's harder to sample from our target distribution, which is a complicated posterior distribution directly. So we would like to sample from something simple and gradually move to the our target distribution of interest. So here is one possibility of the intermediate distribution. So we are introducing another distribution, which is called the reference distribution. I'm using this row to denote the reference distribution because we would like to use something to start with, which is closer to our target distribution. We don't have to start from the prior distribution. We would like to start from some estimate, some distribution based on some estimate from other measures, for example, so it can approach the target distribution more quickly. So that's why we're using this reference distribution here. So basically, we're needing this target distribution with the annealing parameter alpha sub r, and we have this reference distribution, and it has a power 1 minus alpha sub r, and we have this sequence of annealing parameters goes from 0 to 1. So when we have this annealing parameter equal to 0, we have our reference distribution. So that's the first distribution. And we have the last distribution, that is when this alpha is equal to capital R. So this would be our target distribution. That's a posterior distribution. So in the following description, I'm going to simplify the notation by introducing this bold beta to denote all the parameters, including theta de, theta y, c, and lambda. So the algorithm we are using is based on the SMC method proposed in 2006, 2007, and we have this general framework that we start from the first distribution, which is our reference distribution in this case. So we have this set of samples or particles in the SMC literature. So we have this small k denotes the index for the particle. We have k goes from 1 to capital K. So we are using this capital K particles to approximate our intermediate distributions at each iteration. So we update our particles so that we can use the updated particles to represent the new intermediate distribution. So we have a normalized weight, which is denoted by small w here. So initially it's set to be 1, and for the next iteration, so we use a small r to denote the SMC iteration. And for each one, for each iteration, so we sample our particles using this kernel T sub r, which I will talk about it in my next slide. And we got the new particles, and we need to update their weights based on this formula here. And then we can normalize the weights. So if the effective sample size is smaller than some threshold, and we can do a resampling step to get the new particles. So the particles after the resampling are denoted by this beta tilde, and we reset the particle weights. So you can see that the important step in the algorithm, which is to sample the particles. So in this case, so we sample our particles through a pi r invariant MCMC moves. So by using our notation, so that's correspond to capital T sub r in the algorithm. To be more specific, so we can look at the full conditional distribution for each of these parameters given the other parameters to see whether it has a closed form or not. So if it has a closed form, for example, it's a normal distribution, and we just sample from it. Otherwise, if there's no closed form, we implement one step of the Metropolis-Hastings algorithm. That is, we propose a new value for this parameter, and we accept it based on the Metropolis-Hastings ratio. And of course, we can use some more advanced MCMC moves. There's also a backward kernel in the algorithm, which is denoted by this L sub r minus 1. So we choose to use a convenient backward Markov kernel so that it can simplify the weight update. So this is the backward kernel that has been used a lot in literature, and it's also our choice. So using this backward kernel, we can simplify the weight update to this form. So as you can see, it only depends on the particles from the previous iteration. So the subscript is r minus 1. That means it's from the previous iteration. That is, the weight update only depends on the previous particles. Using our intermediate distribution, so this is the form of the weight update. So you can see it relies on the previous particles beta tilde sub r minus 1, and also the difference between the two annealing parameters alpha r and alpha r minus 1. This is very useful because the main problem of implementing the previous algorithm is to decide these annealing parameters. And we would like to determine these annealing parameters adaptively rather than specifying them in advance. So that's why this weight update is quite useful. The criterion that we are going to use to choose the annealing parameters adaptively is to use the conditional effective sample size proposed by Adam and the co-authors. So this is the formula for the conditional effective sample size. As you can see here, capital K is the number of particles, and capital W is the normalized weights from the previous iteration, and small w is the unnormalized weights. As you can see from the previous slide, that this small w only depends on the previous particles and the annealing parameters. Therefore, it's a function of the annealing parameters. More specifically, we already have the annealing parameter from the previous iteration. So basically, you can look at this as a function of alpha r, which is the annealing parameter at this iteration r. So we can determine this parameter by solving this equation. Effective samples, the conditional effective sample size is equal to some criterion which user can specify. So typically, we would like to let this threshold to be a large value close to 1 to get a good estimate. So, which means we'll have more SMC iterations if this phi is a large value. So in our recent paper for another scenario for phylogenetics, so we also use this method, and we did a lot of experiments on the effect of this parameter. So if you are interested, you can look at our paper for phylogenetics. Okay, so that's the our proposed method for doing the inference using SMC. Now I would like to show you some simulation results. So this is ODE with two differential equations. The first one, we have a parameter theta 1, and we purposely using the absolute value of theta 1 to create two modes, and so that we can compare, we can evaluate the performance of our method and compare to some alternative methods. So for the second equation, so we have theta 2 as a parameter, and in the simulation setting, we have a true value theta, absolute value for theta 1 is equal to 2, and the theta 2 is equal to 1. And we needed to specify the initial states to simulate the data. So these are the initial states we are using, which is 7 and minus 10 for x1 and x2 at time 0. So for the observation model, we generated data using normal distribution with mean x and variance sigma square. Here, sigma is said to be a half. So this is the results of from our annealed SMC measures. So this graph is for the particles from ASMC using several intermediate distributions. So we have different colors which represent the particles at different iteration. So the green one are the initial particles, and the yellow one is 1/6 iteration, and this is a half of the total iteration, and we have this one is a final iteration. So you can see, I'm not sure whether you can see it clearly, but there are two black dots which represent the true value. So you can see the posterior particles can cover the true value. So similarly for sigma 1 and sigma 2, so we have this final particles, and this is the true value. In terms of the differential equation trajectories, we have the solid black curves, which are the true x1 and x2, and the dashed red curves are our estimated trajectory using the basis functions. Estimated basis function coefficients and the basis functions. So the dotted the dotted blue curves as 95 credible bands. So how does this method compare to some alternative methods? So basically, our target distribution here is the posterior distribution of parameter theta d, theta y, and coefficients c and lambda. In our case, because we represent the differential equation x of t using the basis function expansion, so we don't need the initial state. We only need to estimate the basis function coefficients c, and we need a smoothing parameter lambda in our model. So that's our target distribution. So in our method, we don't need the DDE or ODE solvers. So we call this method SMC-spline because we use the spline. This is a target distribution, and our implementation algorithm is annealed SMC. But with the same target distribution, we can also use MCMC. As you can recall, in our SMC iteration, we use MCMC moves. So if we use the same MCMC moves, we can just implement an MCMC algorithm for the same target distribution. So we would like to see the comparison for this using the same target distribution but with MCMC. So alternatively, we can estimate the starting state x of t and the parameters in the model, and then we can solve the differential equations using some ODE solvers, so that we get this the x of t. Again, we can use two methods for the implementation for the same model. We can use ASMC and we can use MCMC. So in total, we'll have 4 methods. The first one is our proposed method, and the rest 3 are the alternative methods. So here, as a comparison between for the estimation for parameters theta 1 and theta 2 using the 4 methods, you have seen the performance of our method. It can cover the true parameters. It can find the 2 modes and cover the true parameters. So alternatively, so if we use the ODE solvers, so this is what we get. So for the last iteration, you can see the estimate is pretty close to the true value. However, there's some bias, and the uncertainty estimate is very small. It's likely underestimated. So for the MCMC algorithm, using the same computational cost and the same MCMC moves, it has some problems with finding the 2 modes. Depends on the starting value, it may only explore 1 mode. And it's worse if we use the ODE solvers. So you can see the samples are far from the true values. So here, just a table that delivers the same message, but with some numbers. So the first column are the true values, and the 4 columns after it as a method, as an estimate using the four methods. So for our method, so the credible interval covers the true values we used in the simulation. But for the other methods, so it's may have some bias. For example, for these methods using the DDE servers, so it didn't cover the true value. To take one example, so if we have the true value is equal to 2, and in this case, so the estimate the 95 credible interval is 1.8 to 1.9. So that it didn't cover the true value. Okay, so for the application, so we go back to the motivating example about the blowfly. That's a DDE for blowfly. And in this case, because we're dealing with accounts data, so we're not using the basis function expansion for x of t directly. Instead, we represent x of t using e to w of t and using basis function expansion for w of t. So this is the estimated w of t, and this is the estimated x of t with the observations. So the red curve are estimated x of t, and the blue dots are the observations. So here are scatter plots for the DDE parameters. So we look at the correlation. For example, here we have the correlation between R and P, which is about 0.6. So here P is a parameter for the limitation on the food supply, and R is the rate of population increase. So they are positively correlated. For the estimation for the delay parameter, I'm doing some comparison to the previous results using the frequentist method. As you can see, previously I got a really small standard error, which is around 0.04, and now the confidence interval, the credible interval is from around 5.7 to 9.9. So the uncertainty estimation is, in my view, it's better than the one from the frequentist method, but still it's an ongoing work, and we are working on the evaluation of the quality for the uncertainty estimation. So to summarize it, there are many challenges for estimating the DDE parameters. Our Bayesian semiparametric method using SMC has several advantages. First, we don't need to solve the differential equations numerically, and we don't need to specify the DDE history, and it can provide the uncertainty estimate. And it also shows some advantages over the MCMC methods, using the same moves and with the same computational cost. Okay, so with that, we'd like to thank my co-author, my former PhD student, Shijia Wang, and now he's an assistant professor in Nankai University in China. and the funding agency NSERC, and of course, I would like to thank you for listening to my talk. And please give me any suggestions or comments for me to improve this work. Here are some key reference. Let me know if you have any related work. Thank you.